Hello, everybody. So what we're looking at here is question 4.3, section 4.3, question 5 here. This is going to be a bit of a long one. I'll probably have to do it in two videos. It says a man is walking horizontally at a constant rate of 1 meter per second. So that's this. It's dx dt because I've called this distance here x here. Okay. So that distance is x. And so I've got a -1 there because this distance is closing as he's getting closer to this. And then when the man is at 10 meters, so they're telling us that x is equal to 10 here. And, and basically with that, I can set up the following green triangle here. When x is 10, the height is 23, and the radius, sorry, the angle is determined by tangent inverse of 23 over 10. Okay, because that x will end up being a 10 there. Now, this is actually is the question being asked. At what rate is the angle of elevation changing? Okay, and that's this value right here, this green value that's kind of shows up. That's the rate of change, or d theta dt. That's what's being asked. Okay. Now, when you go ahead and you start this question, you actually have to start with x not being 10. And so you use this red triangle down here to kind of say, all right, look, this is my triangle. This is the theta, and it changes with time. And this is x, and it changes with time. And the relationship between theta and x is dictated by this, according to the, tangent is opposite over adjacent, opposite, adjacent. Now, knowing that theta changes with time and x changes with time, you can differentiate both of them with according to time. Knowing that this is basically, you can kind of pretend like this theta is a whole entire equation with some t's in it. And if that's the case, you kind of imagine, all right, I'm going to take the derivative of this and the derivative of this side as well with respect to time, and you end up with the following. Derivative of tangent is secant squared, and you replace, you're using the chain rule right now. So you're replacing this theta here. But remember, theta is an entire function, and so then you have to take the derivative of that thing and write it here. Okay? But we don't really know what theta is at the moment, so we're just going to write the derivative of theta, which is basically this thing, or d theta dt. And over here, we're going to do the same thing. We're going to take the derivative with respect to time. So the derivative of 23 over x is a negative 23 over x squared. But then remember, we're not taking the derivative with respect to x. We're taking the derivative with respect to time. And so you end up with dx dt over here. If we were taking with respect to x, you would end up with dx over dx here, which would just end up being a 1. Okay. And that's oftentimes what you do. But this time we're taking with respect to time. And now if you look closely at this formula, here, d theta dt is sitting right there. And that's actually what we want. So now you take this and you divide it over, and you have all of this other information already. dx dt is -1, x is 10, and theta is tangent inverse 23 over 10. And when you solve it, you get this value here, okay? When you type that into your calculator. All right. So there's one way of looking at it. I'm going to do the same question in a second video over here, but I'm going to do it instead with d theta dt's. I'm going to actually use the prime notation that we're familiar with. Okay. Our textbook and the AP test and all the videos that you'll find on the television and the internet, they tend to use this method. I do it in this method as well for students at the beginning, so they can kind of see it in a more familiar setting with the primes and things like that. Okay, so I'll do that in a second video, and I'll attach it. All right. How do I stop there? Where is it?